So we're going to talk about how to build reliable machine learning-based services, and we're going to try to give a perspective of how to do it from a black box monitoring perspective. Salim and I are neither machine learning scientists, hacker, or ninjas. 2 years ago, we knew, okay, machine learning is this new thing. So we thought it was going to be very relevant for production services, and then we decided, okay, let's go interview all the data scientists, all the teams at Google and outside Google that have been using machine learning for a while, and let's extract all that insight into best practices, into a bunch of hints that we can use for other teams. We've done probably something like 40, even more, probably even more, something like 60 interviews. And this is basically a summary or collection of all those interviews and all those experiences. However, when we thought about, let's talk as a black box monitoring for machine learning, we said, I think this is the wrong approach. Everything that we've seen so far tells us that we cannot do this, that the way that we need to approach this is completely different. And we think it's better if we talk about machine learning best practices, and for every best practice, we'll look at monitoring. We'll look at what are the metrics that you should put in each of these practices.
Our goals today are to connect these best practices with monitoring and give you five rules for success. Whenever you see this light bulb, that will also clue you in that we've had one of our aha moments, something where during our conversations and our archaeology, we came upon something that we thought was profoundly useful and really want to use that to emphasize our tips for survival. And these tips for survival are to monitor for presence, to ensure that you have high quality data throughout your pipeline, to track resource usage in several dimensions, to instrument your deployments from start to finish, and most importantly, to account for your users' happiness.
Okay, in here, we're going to have several topics that have come up from all these talks. Machine learning is easy, machine learning is new, machine learning is a black box, you don't need to know anything else. You just train once and you're done. You rarely roll back. Monitoring is like any other monitoring. The more data, the better. Just learn all the patterns. It's transparent to user, and compatibility is an op. We believe all of these are basically mistakes, except maybe for more data is better, but be careful, because if you train models with the same data, you might be getting overfitting, so that can be something that if you assume is correct, it might get you in trouble.
As we talked to many different groups at Google and outside of Google, we came across one where our conversations illustrated that they had an important ML model that many of you will recognize. This is YouTube Watch Next. And it's the ML-based system that gives recommendations to users on what video they should watch next. It's been part of YouTube for over a decade, and there's a lot to learn from this system. They deploy continuously and rapidly. Their system has very high accuracy. They collect training data, input data from around the world, from many different geographic regions. And this is key. We'll learn more about this later. It's revenue facing, so there's very high motivation to ensure that it's a high quality product. We have some clear metrics in terms of user engagement with how many videos someone watches when we suggest it, and how they click through on ads. It also is a system that needs to account for one-off events, such as big international sporting events or royal weddings, things that happen infrequently enough that they can skew the input data and lead to bias. And it's also something that's very user visible. So when we don't do a good job with our recommendations, users will notice. They'll either drop out their engagement, but again, rule for survival. We want our users to be happy, so we'll talk about how to measure that happiness. It's not easy to deploy ML systems to production. ML systems are not just another data pipeline. We need to be able to guarantee freshness. We want to ensure consistent user experience across multiple devices as people engage with the product in several different ways throughout their day. We want to do things such as monitor view time and tie that context-aware instrumentation back to some of the more fundamental SRE instrumentation that many systems have. We need to be able to remove bad data. For YouTube Watch Next, this is things like spammy videos or outright bad videos. We need to be able to quickly pull those, not only from being visible, but also from the training data so that they don't recur in the pipelines. We want to be able to deploy regularly, every few weeks, days, or hours, new models, and to have some metric for how quickly these models are loaded. And we're also continuously training models. These models use very different resources from the serving part of our pipeline.
Okay, so the current slide is trying to show what a theoretical machine learning pipeline looks like. At the top, we're basically showing training, and at the bottom, we're showing serving. Training is usually 10% of the effort. People, data scientists, are the ones usually more focused at the beginning on this phase, where you have a bunch of production data. This data is usually offline. You basically do some transformation over this data. This is input data. Data scientists figure out what are the features that are important for me. We build the model that is basically going to compute a lot of resources during training. We do a phase of validation, which basically takes part of the input data that was not used for training and basically make sure that we've got a training model that is accurate enough. Once we have this, we think, okay, we can basically deploy this model to production. That means that serving, we're going to have user-facing requests. We're going to transform the data. We're going to make sure that all the fields that the user is giving us in production are filled, or we impute those ones. Then we do the serving, and serving is basically just getting a classification, an output, and that's being done with the model that we had from the training. However, we believe this is deprecated because this is not reliable, and we'll see why not. Okay, we're going to focus on the best practices that brings us to why that model was not reliable, and we give them in 4 areas. We're going to talk about training. We're going to talk about how data quality is what drives how good your model is. We're going to talk about hardware resources, not because you only need them, but because they are also an indicator. They're an indicator of presence. They're an indicator about how your data grows. And they are also an indicator about the usage in production. As I'll repeat several times, the vital case. You have a service and immediately the rest of the world is using it. We're going to go through a best practice of qualification. How, from a trained model that has been validated, can I be sure that it's compatible in production? Because in production, there's many more things than just your model. There's a bunch of binaries, there's monitoring. And lastly, we're going to talk about deployments, especially backwards compatibility. Many teams at Google, many teams at many other companies had to roll back. Rolling back a model is not easy. It's not something that you can basically decide on a human being. It has to be automatic and requires several checks.
Retraining is a fundamental part of the SRE responsibility in an ML, a system that includes ML. It's important because for any system that depends on an ML component, you've got this big black box where requests go in and then inferences come out the other side. Is what's coming out the other side any good? Are the users happy? Part of the answer to those questions lies in retraining, and the observability for the retraining is key. Training and retraining are an integral part of the entire process, and that's why we're asserting that SRE is very interested in this. It's not debugging or testing. Retraining is key to ensuring that there's fresh data constantly going into the model. We've seen that model loss, that is the quality of the model in the system, degrades over time, leading to lower quality outputs, and what comes out the other end is not as appealing to users. An illustration here, maybe for a photo sharing service. Things are changing fast. Users are taking pictures, uploading them to the service. We want to be able to, as the information comes in, analyze it, apply labels to it, and say, yes, this is Carlos in this picture. And this means that we're retraining with each piece of data that comes in. We're not building a new model for each piece of data, but we are retraining our model as data comes in. In our hypothetical storage photo sharing service, we're probably using a storage layer, and we have metrics there that would be very familiar to you. How much data are we storing? What is the incoming rate of photos to this service? That's all well and good, and you'll see that it goes up and to the right. You should also have instrumentation for the ML component, the number of successful labels applied, that labels are applied to each new object that comes into this system. And that should closely track the rate of incoming data. And over time, that its slope should match the rate of incoming data. This will speak to the confidence of your ML system and the quality of its model. We also have here a picture of a very popular Google service. We've redacted the name. On the x-axis is time, on the y-axis is the age of the model that's deployed. Over 3 weeks, we deployed models very regularly, and the models were never older than X, which is a very small amount of time in the order of hours. And this almost continuous redeployment means that our models are evolving fast, and this was one of the key things that leads to user happiness. We're always adding more data, which provides higher and more accurate inferences to our users.
One of the phases that is key for training, it's filtering. We want as much data as possible, but for filtering, for data to be quality, we need filtering. We need to make sure that we don't have duplicate information. We need to make sure that our pipeline is fast enough so that we can remove a span that doesn't go into the training phase. And we also have to be able to do data imputation. We're gonna have data that is not anymore a binary output. Then now we have 3 or 4 different options. So our pipeline needs to check for that data and needs to impute it. We're gonna have values where we have a null value or a zero value. We need to have those values normalized so that that doesn't produce noise into our training.
It's also important to monitor the size of the data that you have. There are several reasons. First, you need to separate the data that you use for training from the data you use for validation. And you'll work with data scientists on this because the ratio, whether it's 80-20 or 70-30, is very specific to the model. And this is, again, a very context-specific piece of ML monitoring. Reserve that data for validation so that when you are testing the model, and this should be part of an automated test, you're not using the same data that you use for training. You also want to ensure that the mix of data is consistent from one generation of the model to the next to avoid bias or skew that would lead to unintended outcomes and bad predictions for your users. And this should not be confused with qualification. We'll talk more about that in a moment. There's also an issue of training at scale. As the amount of data that goes into your model during the training phase increases, you might hit some very realistic and very boring limits in terms of you can't fit all of that data into RAM on one machine. This means you'll have to shard your model. Sharding the model also suggests then that you'll be loading the model in several different phases in your production serving system. You'll want to monitor latency at that other end so that you know that all the models are loaded before you begin serving from it. And as you're training sharded models, you want to instrument the data coming in so that you maintain the right blend of different inputs from whatever variables your model uses, whether it's geographic area and user preferences, such as YouTube's Watch Next, or something that might be more specific to your model. In summary, you want to make sure that your data quality is correct and that your data is complete. Correctness means that you're instrumenting the entire training phase, that you ensure that you have snapshots and you know how big they are and their age, that you're monitoring the blend of data that goes into each of the models to avoid bias and to present non-skewed results to your users, that you avoid using anomalous data, such as something where all of the data is suddenly labeled funny ad or football match or football game because that's Super Bowl day. You can't use that as the basis for the following Sunday's recommendations. Data completeness means that you want the right ratio of data going into these models, representing all of your expected output users. And you want automation to be able to impute data, to fill in newly discovered fields, to fill in previously null values, And you want to be able to remove biased or bad, spammy data from your data set and disregard it from future training runs.
Okay. So, giving all those insights, especially over the training pipeline, the one that I described before, how does the new pipeline look like? So, again, we're going to have production data that is offline. We're going to have this phase where we ensure data has quality, where we'll start with imputation and filtering data. Then we're going to have several phases of training. We have different phases of training because we might have different values from the data scientists to train models, or because we have different input sets. We might have input sets from Asia, input sets from Europe, and other continents, and we might want to aggregate those data. Finally, we'll go through a validation phase that uses part of the production data that was not used in training, and then we're going to have different trained models at the end. And with these trained models, we'll see that we will take some snapshots because we want to reduce the timing for this phase. So later on, we will see how we add snapshots so that every day you don't have to train data from scratch, so that you can train from a snapshot with only the new data that you have, and you can accelerate the training pipeline. Let's talk about resources. For resources, we usually mean memory, CPU, and accelerators. When we talk about resources, something that is very clear for us is that the resources that you use grow in a disjoint manner. At the beginning, you may think training is the most compute phase, and that is true. However, most of the teams, once they find a certain model, once they don't do more design space exploration, they limit the number of resources that they have in training. And then inference or prediction, when you're serving, becomes the bottleneck for resources. You might go viral, you might have to shard your model, you might have to go to different areas, and that's where you have an increase of your resources. Again, metrics for the resources are a synonym for presence, are a metric that helps you to understand the usage of the service. If you have a suddenly slowdown of the resources that your inference is doing, there is something wrong. There are a number of users that are not coming to your web page or to your service. So that's a way of detecting it. That's a way of doing black box monitoring.
Now let's talk about qualification. The single goal of qualification is to ensure that your service has the right model in the right serving path. That may sound really simplistic. We've talked to many groups who describe the root cause for their production-facing outages, their user-facing outages, as incompatibility between a model and the serving API. So how do you avoid this? Well, you can make sure that you're testing the model with the same version of the binary that's running in production. You can also add instrumentation into your entire deployment pipeline so that you are versioning the model against a particular version of the API, and then add a signature to the model as it's stamped in the deployment phase to ensure that only that model reaches production when a certain version of the API is running. You're also able to tag your model with information about the type of input data, a description of the fields used in that input data, so that you don't have surprises in production when unexpected fields appear. And this will avoid user-facing outages. There are frameworks that also provide the ability to have A/B testing or canary deployments, and this is a must. If at all possible, use a canary so that you're deploying a new version of your model into production for a subset of users. And whether this is a static subset or something that's dynamically chosen is up to you. But this allows you to use that new version in production and to, as you can see in this chart, track its behavior against the established production model. Having presence monitoring also, that is the model up and serving, is important, but this kind of canary versus prod monitoring takes it a step further. Model qualification, what some companies call having a champion model, or what we at Google call using sign models, allows us to ensure that the right version of a model is the one that's pushed to production. And this signature specifies the type of model, its version, along with the description of the input and output data.
Now let's talk about deployments. And when we talk about deployments, we especially make a lot of emphasis in backwards compatibility, being able to have proper binaries, models, and configuration all together. The key points for backwards compatibility are basically to understand that your input data might change. We have several cases where we add new input fields into our production. What happens if your model is not ready for that? So imputing is one solution for that, and alerting over this is another one. Another one that has caused several outages is API changes. If you've used any API for machine learning, if you use TensorFlow, it's a field that is continuously changing. The API continuously changes. So it's a concern for us if you don't have the proper checks so that your model and the proper API checks go together. When we talk about deploying machine learning services, we also talk about fallback mechanisms. And when I say fallback mechanisms, I don't mean a rollback. I mean, as a business case, you need to have a solution when your machine learning pipeline is not working, when it's biased, when it's giving a non-ethical output. You want to disable that completely from production. You need a backup plan for those cases. Google and many other companies have done and will make mistakes about this, and we have to be prepared for that. Again, as we said before, also deprecating all models. How accurate your model is depends a lot on the data. And being able to deprecate models is also a must, because you don't want to give the options to some SREs to roll back to a version that is not good for your service. And three important configuration questions that you need to be able to respond when you're thinking about this. Does your code and model go together? Are they deployed in the same package? The signature is just a mechanism we're describing for this to happen. How do you verify the version that you're running, that they are compatible? Pushing to Canary is a check that many companies and many teams do. Also knowing which API version, and the signature as a metric is an example for this. If we go to a dashboard and we want to check what API is running, we don't want to have to instrument the logs. We want to have a metric that is giving me what model do I have and what API I'm using, and automatically be able to check that. Okay, so given all this information, now what do we believe it's a machine learning pipeline like? So on the top, I'm going to have the training phase. For the training phase, again, relevance on a data quality phase. Data imputing, again, fulfilling fields that are missing, checking fields, and doing filtering. No spam or non-noisy data. We're going to have a bunch of compute. We're going to do validation over production data that was not used, and then the checkpoints that I was talking before. YouTube has a massive amount of information to build their machine learning pipeline. It would be crazy if they have to start from scratch every single day. So what they do, and many other teams, they have checkpoints. And when they have new data, they can start from the checkpoint and adding data. If you need to delete user data or you need to delete the span, you need to start from scratch and then build a new checkpoint. In the middle phase, we have the qualification, which is basically our goal to make sure that this model will work in production. The output is to basically have a champion model with a signature. In here, we'll see SREs wanting to use live data to basically check if your model is working and is giving accurate information. But if you talk to a data scientist, it's going to tell you, no, I don't want live data here. I want offline data so that I can know how accurate is my model versus time, because that gives a repetitive exercise for them and is more valuable. And last, when we're serving, we're going to, again, do live imputation, especially because if we're talking about a front end and we're just developing a backend, the front end team might change your input without telling you. So your data imputation is going to be checking this. It's going to forbid any non-allowed input to go to the model. Then you're going to do your prediction with a champion model and you'll get your prediction. In this phase, we see companies and teams that instead of having a single model, they have one or more. They do A/B testing. They do A/B testing for rolling forward or rolling backwards. But some other teams use it as a check to see which model is more accurate. So you might have one model and a second model. You send your input data to both of them, you get your output, and at the same time that you get your output, you get a metric that tells how the model is confident with that output. And depending on that confidence, you might use one model or another one.
And let's take a closer look at that last part of the, what the pipeline looks like, so that we can take a look inside the model and see what's actually happening. We want to instrument the entire pipeline, the training phase, as well as the live serving portion. We also want to be very careful that we understand the prediction latency. This includes any RPC or framework overhead. And this will give you further insight into the resource usage from your model. You're already monitoring raw resources such as RAM, CPU, accelerators. You also want to account for the time spent in your framework. You want to monitor model aging. We've emphasized that freshness is critical to having a high-performing, highly accurate model. So understanding the freshness of your model is very key to having insight to what's happening in your pipeline. This illustrates what goes wrong when you don't have alerting. This chart shows a deployment for an ML-based service, and the region B, the red line, dips dramatically, whereas region A, the blue line, increases dramatically. This is clearly bad. But wait, is it in fact? No, because region B, at the moment this new model was deployed, had a national holiday. This wasn't reflected in the monitoring. Further monitoring would have led us to see that the user engagement as a ratio remained steady, even though the number of clicks on the service decreased. So the absolute number of clicks is not sufficiently representative of the user experience. Thus, alerting must be domain-specific and understand the experience of the end users, plural, of the system. And these end users may be represented by different metrics. For YouTube WatchNext, one of these metrics is geography. Or for our hypothetical photo sharing service, let's talk about user happiness. And user happiness is not, is Carlos smiling in these pictures? But user happiness is when Carlos opens the app, does it show him all these pictures when he opens the album marked Carlos? If it does, then good. We'll know he's happy because there's no further interaction, that he doesn't search for man with beard, or man with changing beard, or man with helmet. Those would be indications that we collect on application-side metrics that show the user is not happy. Understanding that metric at the very moment of interaction with the user is fundamentally important to having a fully instrumented and well-understood ML pipeline. And we're again emphasizing that model loss increases with age. If there's one thing you take away today in addition to the light bulbs, always have fresh models. So in conclusion, we talked a little bit about how best practices became best practices. We gave some rationale for where you want to add instrumentation in the different phases of your ML pipeline and for different components. We made suggestions about the importance of context-aware metrics and how data imputation helps ensure both fresh and accurate data. We provide a recommendation that you stamp models. This is something that will contribute to production stability as you roll forward and roll back. We encourage you to deprecate old models and to use domain-specific alerting. This is user happiness right there.
And this is what we believe might be the future. We're seeing more and more open source available data sets. You know, those data sets are already anonymized and no need for user intervention to delete data. These are publicly available, they are tested, and you can use them to start as a training set for your models. It's like having a snapshot of your data, and it's super fast. And a natural transition for this is model as a service. For example, AutoML, where instead of building a pipeline for ML, what you have is basically an API. Most of these AutoML APIs are basically just models where you have to train the model with just a little bit of data. They already have a pipeline, so it's much faster, and they build a bunch of reliability services for you. Sharding, replication, etc. Okay, this talk would not be possible with conversation from Alphabet, tech companies like DeepMind, Google, YouTube, Clarifai and ThoughtWorks and many others. Thank you.